Our next speaker is Jiang. Mr. Jiang is from Wanhua Chemical, one of the largest chemical engineering company in China, whose headquarters of this company locates in Shandong province, close to Korea. And our first three speakers all held a chemical engineering degree, and our last two speakers are from control areas. They are all control engineers. Okay. Yeah.
Thanks, Professor Chen. I'm very happy to get this chance to share something we learned and we did in our work. So my talk is quite basic and traditional process control topic. So before let me start this topic, let me introduce some background why we do this kind of study. So you know, in modern chemical plant, we have more and more, I call, protection controller implemented. This protection controller, how to say, just maybe is a simple PID loop, still is a simple PID loop, but the purpose of this loop is not we want to control the process value on the set point. Actually, we want to prevent the process value to beyond the set point. For example, we have a vessel. We're running at a normal pressure at 6 bar, and we have a relief level on this vessel setting at 8 bar. So in this case, we will more and more like to implement protection control. So we setting the setting point at 7 bar, for example. Then if the process value, the pressure go above the 7 bar, we want to open the vent valve to flare or something like that. So this is the intention of the protection controller we call. So the target of this kind of protection control is the dynamic requirement, because this controller, because normally the pressure is at 6 bar, so your setting point is 7 bar. So normally this PID is saturated and the output is 0. So when we have upset from the stream, so there's two kind of case. If it's a sharp upset, big upset, we demanded the controller have a quick dynamic to quick open the blow up vent valve. But in reverse, if the disturbance is gradually and smaller, and the process value is changing not so sharply, is changing gradually, then we don't want the output to open, to minimize some wasting, something like that. So this brings my slide here. So first let me repeat the advantage of the PID, because in these 2 days we have much information on machine learning, neural network, AI. So we still need to spend quite a lot of efforts on the PID, because the PID is still the major control algorithm in that chemical industry. So also the most efficiency is still running based on the PID loop. So this all the PID's advantage. I will not go through detail. So in this slide, I want to explain how currently the industry, the automation industry, they implemented the PID. So actually, the major automation industry, they implement PID like this way. So the most is the reset part. They use the positive network reset component. So they have this is just a first order filter, which come back from the output to the input. So the advantage of this structure is obviously it's quite advantage because you don't need to care about the saturate. As long as the output is hit the limit, the reset function is stopped. So this is the bigger advantage of this kind of arrangement. So you can see, but this arrangement still have face its shortage because the reset function will not released until the proportional part change the signal, which means the negative to positive or positive to negative. And until the proportion part change the signal, then the reset start working. So this is the problem in our protection control because we don't want to have more overshoot on the control performance. So you can see this here. So we have a overshoot here. The green line is overshoot of the silicon. So in this case, it's very much we don't want because, for example, because the overshoot may cause the relief of open. So how is the solution of this arrangement and this function? So in the industry, they propose some automation. They provided the option for the user to define a fixed periload. Is this one. So you can then allow the user to enter a user preload value. So in this kind of arrangement, for example, is the example of what I mentioned, the vessel pressure. So for example, if we have a preload at 20 here, so we don't need the arrow, with the arrow to change the signal from negative to positive or positive to negative. We just need the arrow, the proportion part higher than the minimum, the negative part of the preload. Then the reset will automatically switch back to this direction. So the reset is released. So this can cause the reset part to start earlier to pull the PV back to avoid the overshoot. So this is the arrangement for this preload function. But the preload function still have its shortage because it's not always possible to choose a preload that satisfy different conditions. For slow rate of change in process disturber that cause the limit condition, the preload may too rapid and cause premature control action because the fixed preload is not dynamical change. So next, have a new solution is like this way. So this is the dynamic preload developed this part in the lead circle. So this one can meet our requirement, which can be dynamic preload. So I will so this filter is designed for some noise signals we want to avoid the track action. So we add this filter. So as long as the preload, as long as the proportion part cancel with this part, then the reset action start journey, start moving the output. So it's like this way. Later I will have two page of slide to explain how is this formula is developed. So first let me show you the performance of this kind of arrangement. So we have a dynamic reset simulation test. First we have built a 2 PID loop. It's exactly the same first order lag process and the setting, except the PID recover one is dynamic preload enabled, and the PID standard is not preload function enabled. So both PID have the same PID parameter, and all the derivation action is off. So before the test here, the both controller are saturated. We set the setting pump at 75 and the PV at 70, and the two controller are saturated at the output 0 here. So first, we applied for both PID controller, we applied sine wave disturbance, simulated disturbance with sine wave signals. 60 seconds circle and 10 amplitude to simulate a quick disturbance here. So you can see that this one is the preload enabled. The yellow PV is the yellow, and this color is the preload enabled. So you can see the preload action is quite obviously compared with the standard PID. So the overshoot of the dynamic preload enabled PID is much less than the standard PID. So that's what we want. So second test we did, we changed the disturber circle time from 60 seconds to 300 seconds. So we just simulate gradually change the disturbance. So you can see the periodic action is minimum, is quite reduced. That's what we want. We don't want slowly PV changes, small disturbance changes cause the bubble to move. So this is the test we did. So obviously it satisfies our requirement. So this slide I explain how in the technical basis dynamic preload is developed. So for unconstrained PID with the left gain is 0. Here today to simplify the question discussed, we set we don't want to use the rate action, so set the rate gain is 0. So the PID transfer function is like this way. This is the output equals 0 multiple the processor, the controller gain and the reset factors. Then the output divided by the errors is like this way. We move this error to here. So when the PID is at output limit for extended period of time, the proportion contribution added to the limit determine the output move away from the limit. So the output, when the output is limited, the output is rely on this part, is the proportion part. So actually it's not exactly this way because have a limitation applied on this pair. So when the PID output is not limited, the control measurement and the control output are led to the following manner and the first order. We just assume a first order process. So the PV is like this way. PV equals process gain multiple the output divided by the process time constant. So PP is the process gain and GP is the process time constant. So this formula calculated how is the PV based on the output. So when the output, PID output is limited, the output that would have been calculated if the limit is not imposed may be calculated on this way. So this is the imaginary output if the output limit is not applied based on the current PV value. So this is the idea, actually is the ideal output if the limit is not applied based on the current PV value. So if we assume the control gain is set a lambda factor of 1 and a pure random processor, so we assume in lambda tuning. So the KC is the controller gain is calculated by the processor constant time divided by the KP and multiple the data time plus the lambda is a standard. Okay, okay. So this is the assume we use a no data time process here. So we can calculate the processor gain and controller gain and internal time based on the processor. So the output will be like this way. So we compare with this idea, how to say, imagined output with the real output on previous PID here. So the difference is this part. So we can use this part as a preload factor. So the preload factor is this part. So that's the technical base of the dynamic preload development. So I mean quickly. So this is the central for the compressor. This is a typical bigger centrifugal compressor picture. This a usual machine, and we need anesthesia control to protect the machine. So this is the conception of the compressor surgeon. So this is quite obviously everybody knows. So I will skip this one. So the idea is the anesthesia controller is exactly the protection controller I mentioned. So normally the anesthesia controller will be at a separate status during the normal running, because the current flow is far away from the surgery line. So this is the typical way we implemented the surgery control in the conception. So here is a real plant. We implemented the surgery control here. So this is the compressor performance curve. So this line is the surgery line. So we normally control the anesthesia control line here. So normally around 6 to 10% of margin we implement. So this page, this graph shows the anesthesia control without the dynamic recover. So we can see when there is a 40% demand flow reduced, and the surgery margin is significantly overshoot the setting point, which is quite dangerous. It's close to almost close to the surgery status. So next slide shows the anesthesia control with dynamic recover implement. So you can see the same circuit of 60% demand flow reduction cause the surgery margin not overshoot the surgery margin. And also you can see here the output. Here is the output, the growth valve, and this is the dynamic recover implemented. This is more earlier to open the anesthesia control valve. Okay, thank you.
Thank you.